Hey there, welcome to Caltex Academy. Today on our board, we have some nice integral questions here that require substitution of tangent. So in our previous episode, we looked at 3 videos on sign substitution, and the links of those videos are in the description of this video here. So after watching this video, you can move on and also see how sign substitution works. And with all this said, if you're excited like me, come closer and let's dive into the video. So in our first question here that says, let's have the integral, and for us to have some organized work, we can be using our ruler here. So here we have an integral of 1 over 1 plus x square with respect to x. This is equivalent to, so let's change the variable from x to theta. Now, for us to change this variable, we can go ahead and take something here that, okay, let x be equals to tan theta. So let's differentiate the left hand side and you simply get the x, because we have 1 multiplied by the x, we shall get the x. So the derivative of tan theta is equivalent to secant square theta. So we have here our square theta with also respect to theta, and we have it here. So let's move on and change this variable. So where we have our integral sign, then first of all we need to have the division here, knowing very well that we have a basic question of integration, which is not all that hard. Now x is tan theta, we can replace here tan theta, putting in mind that our x is squared, so we have to also square our tan theta, and that is how we normally write it. So instead of writing the x, we're replacing the x with secant square theta d theta. So we have to multiply this with our secant square theta d theta. So we can also recognize that, okay, now this denominator is exactly the same as what we have here. From this identity, which maybe I can put it down here, that says if you have secant square theta, this is equivalent to 1 plus tan square theta. So having written this, from the denominator we can replace our 1 plus tan square theta with our secant square theta. So simply we have here our 1 over secant square theta times our next secant square theta, which came from the derivative of the tangent here, and this one quickly makes us to cross this secant out, and we are only left with the integral of 1 with respect to theta. And this is now basic integration, which I believe everybody knows it well now, is just theta. Now, since it is indefinite integral again, we have to add our constant of integration. But our question was in terms of x, and here our solution is in theta. So we have to back substitute from what has been given earlier on there. That is, maybe you can recall down here, and we have equals to tan theta. Maybe we can reverse writing it, and we have tan theta equals to x. So for us to get only x alone, we can get an inverse. So we have inverse of -1 this term. So let's make this replacement of theta to get our complete solution here. So meaning the integral of 1 over 1 plus x square with respect to x. So this is equivalent to, instead of theta, we're replacing it with tan inverse. So we have here tan inverse of x plus our constant of integration. So this is our solution of our first question here. And let's move on to the second question, which our second question is saying, maybe we can switch colors. Our integral of this time we have x from the numerator over 1 plus x square with respect to x. What is this equivalent to? As before, we can take our x to be the same as tan theta. So let's differentiate the left hand side with respect to x, and that is only dx equals. We differentiate the right hand side with respect to theta, and that is secant square theta d theta. We also do the same substitution as before here, and we have our integral of the numerator is an x, so we can replace that x with tan theta. So here we have tan theta, and from the denominator we have x, which has been squared, so we can square tan square theta. So instead of writing the x again, we are replacing the x with secant square theta d theta. Now replacing the denominator with secant, because they're the same as we have already seen from first question, we can write it as, let's maintain the numerator, which has been tan theta over, so here we have secant square theta times again secant square theta d theta. If you also replace secant square theta with instead 1 plus tan square theta, is also the same thing, and they will look the same as this down here. For now, we're replacing 1 plus tan square theta with instead secant square theta. So we can move on, and we cancel this denominator with this secant square theta, and we are only left with the integral of tan theta with respect to theta. So we also know that the identity tan theta is the same as sine theta over cos theta. Let us substitute tan theta with sine theta over cos theta with respect to theta. And now the next thing here, let us also change this variable from theta to u. So changing this variable will have u, so it will be equivalent to the denominator, and that is cos theta. And whenever we change variable, we always differentiate. So the derivative of u with respect to u is just 1 with respect to u. And the derivative of cos theta is negative sine theta with respect to theta. So since we have theta here, we have to make this theta the subject of this formula. So we'll have here du over negative sine theta equals to d theta. We simply divided both sides of this equation with negative sine theta. Now this is equivalent to the integral of sine theta over cos theta times, here we have du over negative sine theta. So from here we can cancel our sine from the numerator and this sine from the denominator. But what we have to know here is we have a negative somewhere which we need to take care of in our next stage by putting it out here, and we have the integral of 1 over u. Sorry, we have to replace our u here now with respect to u. So having written this, the next thing here is to just get the integral of this from here, as this is equals to ln u plus our constant of integration. And we also know that u is cos, so we can put here ln u is now cos theta plus our constant of integration. So our solution here is in terms of theta, but the question was in terms of x. So for us to get back x, we can draw a triangle, which triangle can be used to generate the relationship. So let's move on and draw our triangle here. Maybe you can extend a little bit and have our triangle written like that. I think this one is fairly enough. So if this is our theta here, now it is a right angle triangle. From the relationship we had earlier on, that was tan theta is given by x. So meaning this x is over 1, and we know tan is also defined by opposite over adjacent. So our x here is the opposite, x is here, then 1 is the adjacent, x is here, and since we are dealing with cos, we needed hypotenuse. So our hypotenuse here is 1 square, which is 1 plus x square under a square root. So from there, we can write an expression for cos theta. So from the definition of cos, we say cos of any angle theta is given by adjacent over hypotenuse. Now we know that our adjacent is 1 and our hypotenuse is under root of 1 plus x square. So sometimes we may not be comfortable writing with this negative, and again we can change this negative to positive by changing what is inside here using this relationship. So what does that relationship say? We have an identity that if you have negative ln of cos theta plus our constant, this can be the same as positive ln of secant theta plus also our constant, and that eliminates our negative here. So let's do the same thing there. Now if we have written this in terms of secant, so we have ln of secant theta plus c, meaning we have to write this in terms of secant also. So we know that secant theta is given by 1 over cos. So for that case, this one is just an inverse of, we get an inverse of this, and we get our secant as only root of 1 plus x square. Of course over 1, but anything over 1 is itself. So we can go on and we make this replacement here where we have ln of, we get our square root sign here, and we have 1 plus x square, and we close this plus our constant of integration, and that is the solution to our second question here. So if you have got some good value from this video, consider subscribing, like this video to push it to many audience, and then see you in the next video. Peace out.